focus, we'll dive into logical architecture here. So I think there's a fairly broad audience today. So we'll talk a little bit about Arcadia and a little bit about architectures in general. What I won't do is talk through the mechanics of drawing boxes and arrows in the logical architecture. What I think is more interesting and more important is what you're actually doing with the logical architecture, what you're actually putting in there, and that's really the focus of today's presentation. So we'll start very quickly with an Arcadia overview. All right, so Arcadia is the methodology, for want of a better description, the approach that is built into Capella. So it stands for Architecture and Design Integrated Approach, and really it's a way of structuring an analysis of a technical problem, and it includes a series of formalisms, so views, as well as different classes of object that we might wish to show associations between, and it also contains a presumed methodology, which can be quite useful. Like all approaches to systems architecture, it should have an iterative relationship with requirements engineering and requirements development. You do a little bit of systems architecture and you learn a little bit more about what the requirements should have been. You do a few more requirements and you realize that you've missed a few things in the systems architecture. I think one of the strengths of Arcadia in this space is that it has several features that are really quite useful in helping plan throughout the full life cycle, so all the way through to integration, verification, and validation activities. And it is also quite flexible in that you can use it to deal with big problems, small problems, complex problems, bids, and complete architectures for complex systems. So move on again. Okay, so there are four, I think the modern terminology here is viewpoints. When I learned Arcadia, they were called layers. So the first one is operational analysis, and this is all about capturing who the operational actors are. So who may potentially wish to use a system that you're architecting, and what do they need to do. And this quite deliberately has no representation of the system. This is purely talking about what people are trying to achieve. The next layer then is the system analysis layer, where we do a black box style analysis. So we can draw a box around all of the activities that are actually performed by the system, and then we leave the activities outside the scope of the system that are performed by the various actors, which could be people or other systems. And therefore that allows us to identify what's in scope, what's out of scope, and what interactions are occurring across the system boundary. Third layer is the logical architecture. So we'll get to that a little bit later. And then the last element is the physical architecture, which is the design synthesis. So how the system is going to be built. Okay, so operational analysis, just a few more words about this before we go too much further. Again, I'll try and move through this a little bit quickly so we can get to the interesting stuff, the logical architecture. Again, the operational analysis, very focused on who needs to achieve what and what their interactions are with other actors and other organizations. And this layer in particular is quite useful for developing things like concepts of operation. And by doing the modeling in this layer and following the expected conventions in this layer, we can understand the context in which the system sits. And I think that's really quite important. So this provides a good grounding for any further architectural work. So the system analysis, as I mentioned before, it's black box analysis. So we can see that we've got functions that are internal to the system, functions that are external. We can see the exchanges between these functions crossing the system boundary, which then starts to represent interfaces for us. And from here, we can start to derive scenarios, much like we could derive scenarios in the operational analysis layer and start to build up various scenarios of use, or various scenarios that different actors might wish to work through. Here we work through scenarios that show how the system helps them achieve that. So this sort of layering is really quite important if we're trying to define contractual requirements, because they tell us what's in scope, what's out of scope, and what sits on the boundary. Logical architecture, again, this is the last time I won't talk about the logical architecture. We'll get back to that in a moment. And the physical architecture really is all about the design synthesis. So once we've been through the complete analysis, how exactly is the system going to be built? What are the things that need to be procured or otherwise taken further with the design? What precisely are the interfaces? So this is the sort of layer that would be useful in a systems architectural document to define the final architecture and start to help provide delivery teams with the information that they need to go away and build their various components, especially when you've added in the scenarios, which then allow people to see various potential things like interface scenarios that they would have to deal with. Okay, so one of the things I think is very important to remember about Arcadia is that it can be recursive as well. I really need to emphasize that Arcadia, although it is quite often presented as a philosophy where you start with the operational layer and you work out who is trying to achieve what, and then you do the system analysis with the black box analysis, then you work through your logical architecture and then define your physical architecture. You don't actually need to do that. You can do a very quick analysis with all the layers, or you can just stay in the physical layer. Each different layer in Arcadia is just a tool in your toolbox. You don't have to use them all, and that's something I really have to emphasize with new modelers. We can also recurse. So what we can do is we can take an individual component that we may have defined in our systems architecture, and we can take that individual component, that low-level component, and start a new model that is linked to the high-level model where this component is now the system, and then we can further analyze inside that. So that's quite powerful, and it's all traceable. All right, so just a quick word about architectures. So I've pulled out the definition of architectures here. So the fundamental concept, so architecture being the fundamental concepts or properties of an entity in its environment and the governing principles for the realization and evolution of this entity and its related life cycle processes. One of the things that I've actually found, so I think that's a nice definition and lets you realize that an architecture requires a number of different viewpoints. It's not just about physically how it's built, it's about what it's trying to achieve, how it's going to be realized, how it's going to evolve over time. So a few more slides just to try and set the scene before we dive into the logical architecture. I have I like to think about architecture views, so the diagrams, if you like, that show you a window into the architecture model as existing in a three-dimensional space that can be defined. So there are many different ways that you can define it. This is a method that works for me. 3 different dimensions. The first one is the one that we've already talked through, the different architecture layers. So the operational needs layer, then we can scope the project with the system analysis, then we can define the logical architecture and drop down into the physical architecture. So we're sort of adding in layers of detail into our architecture with slightly different purposes each time. But I actually view this as being just one of the dimensions that's interesting to consider. Another thing that's I think quite interesting to consider is the generality of the architecture that you're building. So I've used the example here of a helicopter off the back of a ship. where you might start with a fairly low level of specificity, where you're just talking about in general a comms solution. Then you might add a little bit more detail and talk about a comms solution in a maritime environment, where you might have certain data feeds coming in through your comms system because it is a maritime environment. Then you might consider that you're dealing specifically with comms that have got to go from a sort of home base ship out to a helicopter, and then more specific again, you might pick out a specific class of helicopter and a specific class of ship. In all these cases, you can build architecture views in each of the different layers, as well as each of the different columns here, quite comfortably. And then the third dimension here, which I like to think about, is the maturity. Okay, so I mentioned before that you can actually build architectures in a way that allows during a bid and during a final complete design, and that's what the third dimension here might represent. So a request for information, a formalized bid, a concept design, a preliminary design, and a detailed design. You can actually work through all the different layers and all the different dimensions independently of this dimension, or you can take one of the layers and one of the levels of generality and pick your way all the way through a particular solution. And it's interesting to think about the scenarios where you might pick a not quite specific solution, something that's a bit more general, but then it is high maturity. That might be something like you're developing a comms protocol for the sake of the argument that might be useful in a number of different environments. All right, so what we're going to talk about today, we're going to talk about the logical architecture layer, so the green layer on this diagram, and I feel like the different options for how we might construct our logical architecture layer are best represented by different levels of generality in the architecture viewpoints that we build in how we interpret the logical architecture. So I'd like you to try and keep this in mind as we go through the different viewpoints, and hopefully it will help you decide how much information you're actually going to put in the logical architectures that you might wish to build. Okay, so logical architecture. Now, logical architectures are an interesting concept. I'm happy to be corrected, but I'm yet to find a standard that defines what a logical architecture is. And different approaches, different frameworks have their own different definitions of what constitutes a logical architecture. In Arcadia, we talk about a logical architecture being used to define how a system works rather than how it's built. Okay, so what we want to do is we want to take that initial black box analysis of the system, and we wish to break down the functions, and we want to logically group those functions using some form of strategy. And that's really at the heart of what we're trying to do with the logical architecture. Work out what those logical components are that we use to group together the logical functions in a way that's going to add value, and then work out what those interfaces are between them. And in doing this, we can that's what then allows us to then focus more on what the functional interactions are and how the system is going to work, rather than how it's actually going to be built and the specific components and the specific deployments and so on. It can also be useful in generalizing an architecture. If you have a lot of similar systems that are of the same solution class or product line, you can build a more generic solution using a logical architecture. And you can do a few other things like manage scope between design teams, and we'll talk about that a little bit more now. Okay, so what do we put in a logical architecture? Which is the absolute heart of the question, to which there is the standard engineering answer. which is it depends. All right, it depends on the specifics of your project. There is no one right answer, and that's very important to understand. And that's the reason that I'm giving this presentation, to give you a few options and a few tools that might help you make the right choices. So, what does it depend on? What are the questions that you're going to have to ask? What are the characteristics of your project that might help you to jump one direction or another? So, here are some of the questions that you can ask that I find quite useful. Okay, first the question is, do you actually need a logical architecture? Right. So my current project, we're not using a logical architecture. We're not using it at all because it doesn't add any value. And that's because the domain that I'm working in has a very well understood series of design patterns for each different subsystem. And the scope is well understood. So creating a logical architecture would simply be adding in a whole nother layer of architecture for the sake of a whole nother layer of architecture. So we don't use it. We just go straight to the physical architecture. Okay, so first question you need to ask yourself is, do you actually need a logical architecture? Logical architectures are expensive, and they can add a great deal of value on the right project. They can also be an expensive mistake on the wrong project. So you need to ask yourself, how well is the solution already understood? If the solution is really well understood, you might need to think twice. Or perhaps part of it's understood and part of it isn't. You might need to ask, and one of the most important questions is, who's going to use the logical architecture? Who are your stakeholders? How are you going to help them work through the life cycle, their engineering life cycles? Right? Because again, we don't build architectures for our own benefit. We build architectures to help other engineers do their jobs. Okay, you might need to ask yourself, do you have multiple site deployments or multiple platforms that you're building your architecture for? You might also need to ask yourself, how well is the scope of each different design team understood? Sometimes that's clear, sometimes that's not, and depending on how the teams are broken down, and how much help is actually needed for the project. When we ask ourselves, what value are we going to add, and we're asking ourselves how much is already known. So the sorts of things that we need to be asking ourselves are, how well is the scope understood? How well is the solution class understood? So is it a rail line? Is it a metro line? Is it a container port? Is it an airport? Or is it an entirely new system that hasn't been built before, like the things that Elon Musk is trying to build and fire off into space? That's not an overly well understood solution class. How well understood is the general solution? So if you understand the basics of the solution class, you might, the next question then is, how well is the general solution that you're applying to your specific scenario? How well is that understood? How well understood are the requirements? Do you have a tight set of requirements, or do you need to help develop those requirements? How well are the interfaces between the different work packages defined, or presumptive subsystems? What are the overall functional dependencies? Do you know them? And do you know what your overall safety case is? So again, these are the sorts of things that you can ask yourselves, and you can ask the team, that help define what it is that you need to put into your logical architecture. Okay, so I think I mentioned this before. Too much architecture is too much. It will be expensive, and people will stop seeing the value in it. So if you don't need it, best advice I can give you is don't do it. All right. So, when we look at things like requirements, interface documentation, integration, and verification and validation, we can dive down into that, and we can ask, well, which areas do we need to help out with the requirements? how much help is needed with the interfaces. Again, particularly software-centric systems tend to not be well understood, even if people think they are. So when there's scope breakdown that needs to happen with infrastructure projects, even though people know what the technical solution is, sometimes that boundary between people pouring concrete one side of a line and people pouring concrete on the other side of the line is not so well understood. And when it comes to verification, validation, and integration, how many scenarios do you need to define to help people work through that phase of the life cycle? So I mentioned multiple platforms. It's interesting to consider what the differences might be when you're deploying multiple different systems. And if you have things that are different enough and complex enough, there may be value in having a logical architecture that gives you that general solution that you can then manage perhaps separately to each individual deployment. And the design team scope will get to that in just a moment. Okay, so now let's get into the heart of the presentation, the different types of logical architectures, as at least I've defined them and I find useful. So this for me is a key slide. So these are what I call the different types of logical architecture: scope breakdown, solution class / what your solution class options might be, a detailed but technical agnostic solution, so like the product line type architecture rather than the specific deployment. And then we've got a deployment agnostic solution where you already know what all the components are, but you might be deploying them to a different site or a different platform which has different requirements. A classic example here is CCTV. You might know what all the different cameras are that you wish to deploy, and you know how that's going to tie back to the head end units and all that good stuff. But if you're working on a rail project, your stations will be different, and so you'll have different deployments and requirements for your cameras. So what you end up with then is a need for a general solution to be defined, but not a specific deployment. And then the last one is a specific solution. And that tends to be a little bit more useful when you don't actually need a physical architecture, and a logical one is good enough. Software is quite well aligned with that last option. Okay, so as we dive into the logical architecture, we need to ask ourselves a few more questions. Once we've understood what the problem is that we're trying to solve, by asking what's actually needed, we then need to ask ourselves, well, what exactly is a logical component going to represent? What exactly is a component exchange going to represent? What does a functional chain represent? What does a functional exchange represent? It's expensive to put these things into your logical architecture, so you need to have a reason for doing it. It's got to add value. If you're putting it in to have a nice, complete architecture, you'll be doing an awful lot of modeling and providing not much value. So you need to think about specifically each time you put something in your architecture, who cares about it? What value is it giving them? How is it going to be used? Every time. Okay, apologies, there's a slight artifact on this slide. That's my fault. I apologize for that. Scope breakdown is the first type of logical architecture. We'll have a look at an example and have a look at what some of those components or what some of those elements of the logical architecture might represent. So we do this when we are using logical components to break down the scope of the system. We might have a reasonably well understood technical solution, but what might not be clear is who's going to be doing precisely what. Again, a rail line's a really neat example of this, where there might be some confusion and lack of clarity between let's say a work package focused on stations, and then maybe a work package focused on the line, what I might call line-wide type systems, or perhaps there's a separate work package for security and CCTV. Where is the line drawn between what the security team is doing and what the comms team might be doing? So in this case, when we break things down this way, we do it because we're already confident that we understand what the technical solution is going to be. So we're not worried about that. What we're worried about is understanding scope. The interfaces, they tend to end up representing interface requirement specs, and the functions will end up mapping to contractual functional requirements for each of the work package teams. Okay, so here's an example of what our logical architecture might look like. And our in this case, to the left, what we can see is we've got an external actor. To the right, we've got another external actor, and in the middle, we've got a stations work package and a line-wide work package. And in this scenario, okay, so we can see that the functions themselves, they would map to a functional requirement that needs to be delivered by the work package teams. When we look at the functional exchanges, they would map directly to interface requirements. So each different functional exchange that we draw, we need to think about how that then maps to an upstream or downstream functional requirement, and what that interaction needs to be between the different work packages, or indeed the external agreements with stakeholders. In this scenario, the component exchanges, they represent the IRSs themselves, and then the functional exchanges, they represent the individual elements within that IRS. Also, in this scenario, if I just move on to the next slide, mapping between function ports and component ports adds very little value. Right? Why? Because there's only ever going to be one IRS between the different work packages, so you don't need to understand which IRS is mapping to which functional exchanges. That's already clear. You're not really adding a super amount of value. And in this approach, your functional chains, they will map, roughly speaking, to capability realizations. So somebody will have some form of ConOps somewhere, and it will talk about how a particular capability needs to look, and then in this scenario we understand which work package is delivering what functionality to help us achieve that. Okay, so the next is the solution class. This is what we do if we are trying to potentially compare different solution classes. So one example might be heavy rail versus metro. Another example might be raw radar versus GPS to track the location of an aircraft. So fundamentally different solution classes there. That'll help us identify what the sort of general requirements might be for top-level major interfaces and subsystems, without selecting specific solutions, specific vendors. So this is genuinely the the top level, how does it work, not how is it going to be built, sort of option that we talk about in the actual training for the logical architecture. So useful when you want to when you're putting out a tender to see what solutions people might come back with, and it's also useful if you want to look at a couple of different options without going into too much detailed design and to build a solution. You can solve some problems and identify which solution class is going to be useful fairly quickly. All right, so what does that look like? So I've got a couple of different images here. Solution class. So what we can see is we've got, in this case, we've got two different technical solutions. At the top, we've got an aircraft, a radar sensor, an air traffic display, and an air traffic controller. On the bottom, we have an aircraft which has a radio that's sending ADS-B messages to the air traffic display and then to the air traffic controller. So on the one hand, it's raw radar bouncing off the aircraft, and in the other case, you're sending a message, perhaps a GPS message, detailing where you are. So two totally different technical solutions that we've modeled to compare which one might work best for us. And in this case, the functions represent the basis of a top-level technical spec. The component exchanges, they would represent the IRSs themselves, but this time it's between the major subsystems rather than between contractors. The functional chains, they help us map through what or how the technical solution will actually achieve the desired top-level requirement. So we can see that here we've used the same components that come with the logical architecture in Arcadia, but we've used them for totally different things, and they represent totally different things, and they can. And what's important here is what the stakeholders in the architecture will actually get out of the model. So we've moved on just a little bit here. So in this case, you might actually have multiple different interfaces between the subsystems or external elements. So now the mapping of the function ports to the component ports, that actually starts to help define for you what the scope is of each of the interfaces. And we're starting to now see how a scenario might explain how the technical solution is actually going to function. And then you can start to ask yourselves some questions like, is the dynamic behavior going to be good enough for us? So the next type that I wanted to talk about was a more detailed solution where we're not looking so much at the solution class level. We're now going into some finer detail. And typically we might want to use these if we already have a reasonably well understood solution that people have typically rolled out multiple times. So we can add another level of an extra level of detail here. So what this means, what this means is that you can have the one architecture, and you can have the slight variations between different deployments, and they don't matter because you've built a logical architecture that helps you understand the fundamentals of how things are supposed to work. So you can have a common architecture across deployments with the maximum amount of detail that you can achieve in that. You can leave the specifics to the physical architectures for each deployment. Is reasonably resilient to technology changes, obsolescence, and adaptable as new solutions come through. All right. So here we have an example here of another solution here. So this is a solution where we're tracking things that are occurring around a ship. So we can see on the far left-hand side here, we've got an aircraft, a ship, and a submarine that are doing various things, and we can see that the ship is taking in that information via, at the top there, a radio sensor, then a radar sensor, an aircraft, or an aviation sort of radar sensor. We've got a navigation radar to work out where the other ships are around, and we've got a sonar sensor there as well as the radio to receive messages, perhaps an ESB message to let us know what's going on. We can see that there's a track fusion system and a comms system that are working together, and then we have a data bus, and then we've got an air traffic display, and we've got a tactical picture display as well. All these sort of different bits and pieces that might you might be able to analyze and understand and deal with in the logical architecture layer, but you haven't decided on which radar, which sonar, which data bus, who's going to build the consoles that people need to sit in front of. None of that is defined here. but you can certainly work out a lot of the detail about how the system is going to work. So in this scenario, the functions now, they represent something that might fit better into an allocated baseline. So not the top level functional requirements, but now the next level down. We can see that the interfaces themselves, they represent the interface descriptions between the different components. We can see that the mapping of functional exchanges to component exchanges is now not just a good idea; it's essential. So you know precisely where the flow of information is going, and the functional chains, they now represent the top level functional requirements that in some of the earlier architectures may have been represented by a function. Right, so this is a different way, a different level of detail that we might wish to add. Okay, so now we're looking at functional exchanges being mapped to instead of top level, perhaps external from the major subsystems viewpoint requirement specs. We're now looking at internal requirement specs and so on. And now we can see the required sequencing of messages that might help us to achieve the outcome that we're looking for, so we can then start to evaluate various vendor technologies in terms of selecting the actual physical solution. All right, so the next level of detail in generality is what I call the deployment agnostic solution. Very similar to the previous one, except what we do here is we've actually already selected the components. Now, arguably, you could also do that with a rec in the physical architecture layer, take a recording of an element of the physical architecture and deploy that. But you could also, you can also do that with the logical architecture. You can also achieve a similar thing with the logical architecture. So here is a scenario where you have you know exactly what the technical solution is, and this is very much the case like the CCTV, where you've got a defined solution and a range of different options, and perhaps the same thing can be said for HVAC or network solutions in the infrastructure space. All these things you would say, here are the range of components you're allowed to have. Here is how they're going to tie back to the head end and then tie back to base somewhere. But what you don't know is how you're going to deploy that to this station or that building or this platform and so on. So that's the part that you don't deal with. So let's go and have a look at some of the architecture here. So what we can see here is that rather than a general camera solution here, we've got a specific type of camera. Here it's an Acme camera with 170 degrees of view, and it's an outdoor camera. So this is the one that you would deploy to the outdoor camera, to an outdoor environment, and it then needs to connect via the Acme video networking solution that will then tie into the Acme head end, and then there are some other options there for things like pan tilt zoom cameras and indoor cameras as well. So this is how you would build up that sort of solution. This sort of architecture, it doesn't define the physical architecture for a physical deployment. It simply says, look, here's how we're going to tie everything together in general, and then let the physical architecture sort out exactly how that's going to happen. So in order for that, the technical solution needs to be really well understood by each of the design teams. Right, the components represent what needs to be procured, and the functional chains here, you could use them as to represent requirements, but they're also going to be useful here for integration sequencing. So what needs to exist and be available for you to integrate the next component. All right. So in this case, some of the interfaces might be interesting for management between different teams. Others of them will be internal to the responsibilities of a design team. Okay, and then the last one is where you just define the entire solution in the logical architecture. We have the ability to build a logical architecture where you, and this typically works best with software, where the components that you define in your logical architecture, they're the components you're actually going to build. You don't need a physical architecture, because that might be a waste of time, particularly if you're not deploying a new piece of software to a specific location. You're just building the software, and then the physical deployment, that's for somebody else to worry about. So we can define the individual software component, we can define the interfaces, we can define classes and exchange items and so on for each of those individual interfaces. There's also probably an argument where you might ask yourself, well, how much should I be doing in Arcadia, and how much should I be using a UML tool for? That will depend entirely on your particular project. Okay, so we talked a bit about how we can interpret the different elements on an architecture diagram. The other thing I want to talk about, because this is something that's caused me grief in the past, is how we organize functions and how we organize functional chains. I've seen people organize them in ways that are different to this, and what that's resulted in is confusion about where a particular function needs to live in the hierarchy of functions, and we end up with duplicate functions or overlapping functions, or part of a function in one place and part of a function in another, and that can get very messy very quickly. My recommendation is, when you don't understand the technical solution, to organize your functions by individual discipline or design teams. Okay, you won't go too wrong with that. When the technical solution is understood, organize them by subsystem. Right, that neither of those is particularly intuitive if you take a purely functional view of the world, but I think you need to take an external from the functions point of views, be that team organization or technical solution, to help you organize your functions properly. So highly recommended. Functional chains. So I would strongly recommend that you keep your functional chains organized in a similar fashion. So keep your functional chains with the functions that you've used to tie together to build your functional chain, and then have a separate section for your effectively your whole of system functional chains that should be using all of your lower level functional chains as constituent elements. All right, and then the final thing to say is, if you're still not sure after we've been through a number of these slides, a couple of things I would say. Maybe what you actually need is a hybrid. Maybe you need to define a work package over here, and then dive into a little bit more detail for a work package that you're more interested in, or isn't as clear. You should always use your engineering judgment. I'm always happiest when I feel like there's a strong alignment between every line, every box that I'm putting in there, and something somebody else needs. If I find myself having to take multiple steps before I've actually achieved something that's going to be useful, I always feel like that's not quite efficient enough. So one of the things that I like to do is to ask myself, all right, if I was to use a script to generate a spreadsheet from the model, would I actually produce something that somebody would actually need? And if the answer is no, go back and rethink what you're doing. So I'll leave you with my favorite little saying, which is, remember, all models are wrong, some are useful. Know what the problem is that you're trying to solve. Okay, that's about asking what value you're going to add. Know how the model contributes. That's about understanding how you're going to use each of the different elements, and not expecting the model to provide all the answers, just what it's efficient to use the model for, and know when to stop, right? Because modeling is expensive. Okay, so I think that's the last slide, except for thank you. So thank you for listening to me. I hope you got something out of that. I hope you find that useful. I hope that helps you better define your next logical architecture, or indeed choose not to build one at all. So over to you, Romain.
Thank you very much for this presentation, Tim. So actually, we have a few questions in the chat. So
Yep.
in addition to domain understandability, doesn't logical architecture also help in fast progressing domains where tech is fastly changing and we need a layer that sits on top of physical architecture, which can change in a couple of years?
Yeah. Okay. So I guess I think that's interesting. I think it's I alluded to that without saying that specifically. The idea of having a logical architecture that covers the solution class that you can then manage at that level. I think I went about as far as saying you can manage it at that level. The Depending on what you want to get out of it, you might find that you need to raise up the level of the logical architecture a little bit so that the tech can change underneath it, and you still have a good understanding of how the overall system needs to operate, regardless of the technology. Alternatively, if you want to try and capture something that's a slightly lower level, then yes, you absolutely can use the logical architecture to capture um, how the latest and greatest systems work, regardless of what was physically deployed a few years ago, and that can then keep a hold of the model um, that tells you how you need the next system to be deployed. So yes, absolutely, that's another use case.
Okay, so another question from Christian: can function to logical allocation matrix show multiple solution classes and reflect a coverage? How well different solutions were explored?
So kind of functional to logical allocation. So we're mapping functions to logical components, uh, show multiple show how multiple solution classes reflect coverage. Yeah, absolutely. That's one of the things that you can do. In fact, that's one of the things that I find really useful in using the Arcadia framework, is when you take all of your functions and you try and find a home for them. Do they fit in that box, or do they fit in that box? You can very quickly work out which ones don't have a box to fit in. And then you need to work out whether or not what you actually need to do is break things up and put one bit over there and one bit over there, or whether you actually need a new, a completely new box. So, absolutely, that's something that can be quite useful when you're evaluating the different solution classes, and you can therefore fairly quickly, with a light amount of modelling, work out whether a solution class is really a viable option for you or not, if it's not going to do all of the things that you need it to do.
Another question from Nikhil: can logical architecture be used to develop an N2 interface matrix?
Absolutely. But the question is, what do the logical components represent? So absolutely you can do that. And the really interesting question then is, what is the value that we get out of the n-squared matrix?
Another question from Ahmed. I would love to see each type of logical architecture in context of the full workflow. Can you share links to models for worked out example systems with enough complexity to benefit from applying the methodology? So I think that should be a question for me for after the webinar. But thank you for this question.
Yeah, no, I don't have such models shareable. But yeah, look, I think one of the interesting things that I think we all need to be thinking about as people interested in modelling is building up industry-wide, depending on whatever industry you're in, libraries of reference architectures that can be useful for the next project of a particular type. And I think if we can build up as a community of systems engineers, a global knowledge base of reference architectures, then I think that would be very, very useful. I know that's not quite the question that was being asked, but yeah, I think reference architectures are part of the answer.
Yeah, thank you. Thank you for that answer. So a pretty long question, but I will try to
Okay, I'll try to answer it.
to shorten it a bit. So, yeah, it's pretty simple. As I understand, the Arcadia MBSE methodology is often used to design large and complex systems. But how does it work when the problem is just a small and simple system? So then take the example of an electronic throttle control system. And so the final question is, and the second question I would say, in this case, what would be the difference when applying Arcadia, Capella, and MBSE in comparison to traditional approaches? So
Okay,
two
all
questions
right.
in one, in a way. Yeah.
So first of all, I don't know when the question was written, but I would definitely refer you to the last slide in the presentation, which states know what the problem is you're trying to solve, and B, know how the model is going to contribute to that. If you have a very, 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 very simple problem, do you need a systems architecture at all, or can you simply dive into a discipline-specific design? Right? The I think what you need to ask yourself, if you've got a specific scenario like an electronic throttle controller, is have you defined all the scenarios that it needs to operate in? Do you know what the interfaces are? And do you? And when I say scenarios, it's interesting to consider things like states and modes as well. So what are all the different things that you might be interested in? And you might only need a very small architecture. So it doesn't work any different. You just maybe not. You don't need a large a large model. I think that the Arcadia methodology again is very scalable. You can just focus in on just a little bit and get the message across. In order to prepare for this presentation, I built some very simple models, and I presented them, and I've done I've communicated what I wanted to communicate. So the model worked for me. Maybe you need a similarly small model. Maybe once you start doing some scenarios, you might discover that there's a few other nuances that you can pull out and help show other people who might be interested in interfacing with the electronic throttle control unit, what it is they need to be doing as well. So I would say same, but if it's smaller, then you just need less of it. So in terms of comparing Arcadia to traditional approaches, more and more I'm kind of rejecting the idea that there's such a thing as traditional versus model-based, right? Model-based is just systems engineering using modern tools. Why should architects get all the fun and get to use all of the 3D tools and build their 3D models that solve physical complexity, and not get told they're doing model-based architecture, and get told they're doing model-based architecture instead of traditional architectures. When systems engineers, we build systems architectures using models. Reality is everybody should be using computerized digital systems now. And I think the days of document-based engineering approaches, regardless of whether you're an architect, a mechanical engineer, a systems engineer, a rocket scientist, documents are gone. It's just we're using modern tools to do the same thing. The great thing about using these modern tools is that you store all your information that is pertinent to the job that you're doing in one place, and all of your views should be nice and consistent, which you just don't get out of a document-based approach. Hopefully I didn't ramble on for too long.
No, it's okay. Thank you. So we still have time for some other question. Okay, so a question from Ketaki. How can we do system level V&V in this tool? I've heard of Puzzle. And what sort of V&V can be considered at logical architecture or system analysis layer?
Okay. So system analysis layer, I think it's easier to answer. System analysis layer, that's best suited to contractual level modeling, contractual level requirement, and therefore contractual level V&V. Logical architecture, it depends on exactly how detailed, how much or how general your architecture ends up being. All right, so we went through a number of different layers. In terms of doing V&V in the tool, I don't think we do V&V in Capella and using Arcadia. I think what we do is we prepare for it. So we do the analysis of how the system is going to work. We produce the scenario diagrams, we produce the interface diagrams, and so on. And this tells people what they need to test and what the expected behaviors should be. And then that they will do using ideally the built system. And if you can't do that, some other form of analysis. And then you would record that in one of the various V&V tools that are out there, which could be as simple as DAWS or Excel, or as complex as HP Quality Center or the rational tool, whose name I forget, and so on. So hopefully that answers the question.
Yeah, thank you. So, question from Joshua. So, what do you see the role of the logical architecture is in multi-level of abstraction system models? For example, an aircraft to engine control system. How best to use logical architecture to coordinate design effort at each layer?
Yep. Okay. I'm going to answer that question by saying I don't think logical architecture layer is necessarily the right answer here. I think what you're doing is you're taking a complex system and then you're breaking it down into smaller and smaller pieces. And if you wish to do in-depth modeling of an aircraft, you can define how an aircraft works, and then you can take a component and you can do a transition and make the engine the system. So you do a system analysis layer around the engine using the I think it's using the system to subsystem transition facility. Then you can work out how the engine works, and you can break it down into your individual physical component elements, including the engine control system. And then you can take the engine control system and do a system to subsystem transition, and you can make that the system analysis, and then you can break that further down again. If you wanted to try and do this sort of thing using layers of abstraction instead, layers of abstraction work in both the physical architecture and the logical architecture. Okay, so you can have parents of parents of parents of parents of parents in terms of components in the physical layer and also the logical layer. So I would argue you've got a range of different tools there, and the logical architecture may not necessarily be the right lever to pull as such in terms of breaking things down. But you may find that you do have a technical solution agnostic logical architecture layer where you've got several layers of abstraction. That's up to you, but I do strongly suspect in this case that the system to subsystem transition is going to be what's going to help you the most. And bear in mind that layers of abstraction work in all different architecture layers.
Okay, thank you, Tim. Is there the possibility to create a connection between the development/modeling in Capella and the project for railway system? Can I use Capella to model software accordingly to the normative EN 50128?
Yes, good question. Very good question. I'm not going to immediately answer that here because there are a lot of requirements in EN 5128. I have no doubt that with enough time and planning, we can work out a a modelling strategy that would work and be compliant with EN 5128 requirements. But it's just a question of time and money and effort. There's no magic button to say, produce for me a EN 5128 compliant architecture. You'd need to use the right elements in the right way to produce the right reports and the right views. Qualified probably is the answer.
Okay, so do you have any advice to simplify logical architecture diagrams? I have recently started exploring this layer. Any other pointers outside of deleting unnecessary information?
Yeah, good question. If you're looking at a logical architecture diagram and it's looking overcomplicated, then it's not filling your information needs. So I would go back and ask yourself, who needs the information? Am I providing the right information? So it's kind of looping right back to the beginning and ask yourself, what are you doing this for? My immediate reaction to, did you have any advice to simplify logical architecture diagrams, is remember the rule that every single thing you put in a logical architecture, or any other architecture for that matter, has to mean something to somebody. All right. So if you are focused on what it is that you need to produce, if you are focused on only putting information in to a view that will be useful for somebody, and only putting in individual objects into that view that have a specific meaning for one of your stakeholders, I think that you will find that your diagrams will naturally be simpler. Other things that you can do, I guess, you can take multiple copies of diagrams, and actually one of the things that that I have done in the past is have one great big working diagram. I then copy and paste the format into a new diagram, and copy and paste. No, copy and paste is the wrong phrase. Pull in a couple of elements from that large diagram, and then copy and paste the format from the large working diagram. So that way, I sort of lay everything out once in a sensible fashion, and then I copy and paste the format, not the objects. So maybe that's something that might help you.
Yeah, thank you very much for joining, everyone, and thank you, team, once again. And have a good day and a good night.